Chapter 2 begins the organization of chem study, as you can read as well as I can. But the idea is, how do we study such a complex system? Uh, Basically, chemistry is study of matter. Matter, as many of you know, by definition, three stripes is by definition, anything having weight and occupies space. So what does that point to? Everything. So in studying chemistry, we need to organize everything into something that is a little easier to digest in portions. And that item that we need to start with is the simplest form of matter. And so in order to understand how we start with the simplest form of matter, that is, well, it can be even simpler than what I'm about to say. Fundamental particles, protons, neutrons, electrons, build the atoms and so forth. That's where we will really start. But how do we get there? Well, first we need to classify matter in a way that shows how the course is broken down, or the study of matter is broken down. Matter, make a little table here, is broken down in two major areas: mixtures and substances. When we speak of mixtures, the essence is a physical combination of chemicals or items. You want to get esoteric about it. When we talk about substances, on the other side of this diagram, we're talking about a chemical process and what have you. So in the study of whatever we're looking at, the idea is to break down the mixture side of this diagram and the substance side of the diagram into the more fundamental particles, and then start there and build back up. Because we can study the simple first and then build to the more mixtures are in themselves divided into two areas: homogeneous mixtures and heterogeneous. Now, both are prepared physically in that you are mixing components that do not change their chemical makeup. When we talk about a homogeneous system, we're talking about something that has consistent properties throughout as far as the definition goes. Whereas the heterogeneous on the other side of this equation is inconsistent. Throughout. What this implies is a uniform distribution of concentration is the main focal point. Of items making up the mixture. And a non-uniform distribution in of concentration in the heterogeneous. Now, the simplest one that we can talk about in terms of mixtures is the solution as one of the types of the mixtures. These are essentially defined as homogeneous mixtures in themselves. In working with homogeneous mixtures, you can sample the mixture at any point in the combination, and you'll find the percent composition will always be consistent. Now, the expression of this consistent concentration is like a density term. In the following way. So homogeneous solutions and the distribution of the components of that homogeneous solution are expressed in terms of what we call concentrations. For solutions, by definition, is an amount of solute divided by an amount of solution. Now, the amount of solution can be expressed in either a mass function or a volume function. But it is an amount in terms of mass per unit volume. If you recall the density is defined, D equals mass over volume, then we'll have concentration is equal to mass of solute over volume of solution. Now, this is the mathematical way the distribution of the components are defined. You can define it, actually the solute is the component in least amount in the solution mix, and the solvent is the component in a greater amount. That is, the solution is a solute plus a solvent. So when we talk about this, both of those are contained in that denominator term. Now, we'll be using concentrations in many ways. Earlier we did a quiz question, concentration of NaCl in solution was given to be 25%, and we'll put W/W. That means it's a weight-weight ratio. So it's 25% of the total solution is whatever the concentration is. And so you can see how we're using this idea of expressing defining solutions using this mass component divided by the total mass of solution. That is, here, if we expand this, the 25%, as we've seen earlier today, is 25 parts of sodium chloride in 100 parts of solution. And in that context, and you convert that to parts to, you can use grams over grams here, in a weight-weight ratio. And then, if you got a density of the solution, you can convert it to a volume. So you can go one or two ways here. grams over volume or grams of solute over grams of solution or volume solution, grams solute. So, you can express it in those different forms. Now, what am I trying to teach you here? I'm trying to teach you one of the arms in the study of matter is this mixture, okay? And one that's most frequently studied is solutions. And how do we express these solutions is in terms of what we call concentration terms. And that's always defined as an amount of whatever you put in the solution over the amount of solution. So it's part over total all the time. And so this is just showing you how we work from a bigger idea to a more concentrated idea. And that's as far as we go at this point. Now, I'm expecting you to understand the percentages. That's about as much as I've explained in terms of applying the math and some concepts. Now, when we talk about substances, all substances are homogeneous. And the term substances in our world of chemistry is divided into two areas: elements and compounds. Now, the terms that I'm about to use are synonymous: elements or atoms, compounds or molecules. When we are talking about issues in chemistry and we wish to talk about elements, when we apply the word atoms, we're talking about a single entity having a certain structure. When we're talking about elements, we're talking about many of those individual entities. So it's a multiple issue when you go to the elements. It's a single issue with atoms. Same issue, same idea with compounds. Compounds. When we talk about compounds, we're also talking about molecules. But you should keep in mind that molecule represents a single structural entity, and a lot of molecules represent the compound. And so it's more semantic issue in how we deliver and explain and discuss the issues. Now, when we talk about elements and we want to break it down to even simpler forms, they're really elements broken down into three types of elements, and we will get very detailed in this chapter on these types. You have metals, metalloids, and nonmetals. When you look at the periodic table, you can see these in terms of, for any periodic table, this is one form. This little staircase is the focal point right now. And it divides the types of elements. Those on the left of this are metals, and those that are on the right of it are nonmetals, and those that touch the line are metalloids. So if we look at boron, silicon, aluminum, germanium, arsenic, antimony, tellurium, polonium, astatine, those are metalloids. They have properties in some cases like metals, properties in some cases like nonmetals. However, once you get past that over into this region, when you start talking about carbons and nitrogens, phosphorus, sulfur, chlorines, fluorines, bromine, iodines, and so forth, these are classified as nonmetals collectively. And they have their own set of rules and regulations of how they behave. On the left side, you'll see all the elements not touching the line, including this double green bar down here of elements, are metals. And they have their own set of rules and regulations how they perform. And so as we get deeper into this, we will itemize those rules of how the elements and atoms of a given element perform and why it performs as it does in chemical bonding and making molecules and so forth, like that. So we're breaking it down to the simplistic issues, making it a point, giving us a point to where we can start studying and digesting material systematically. The other side of this little equation here on organization of matter and study of matter are your compounds and molecules. When we talk about compounds and molecules, they themselves are divided into, well, two primary areas. Ionic compounds, CPDS is compounds, and molecular compounds. And we'll see that the formation of the molecule is based upon the combining of either metal and a nonmetal or two nonmetals. If we have a metal from the left side of the periodic chart plus a nonmetal, we'll have an ionic compound. An ionic compound, if you know, is a substance which, when placed into water, ionizes and breaks up in cations and anions, or plus negatives, and floats around in ionic form. Molecular compounds are those compounds made up of two or more nonmetals. They do not ionize. And they have certain behavior and properties and characteristics that we will study in great detail, and how to untangle the mystery of what a molecule will do by looking at certain properties within the structure of that molecule. Elements, the smallest entity of a substance that has specific chemical and physical properties. And cannot be broken down by ordinary chemical or physical means. Now, what I mean by ordinary chemical and physical means, that is the application of heat, light, and electricity. Now, the limitation of this last statement is that while chemicals or elements in the chemical world undergo reactivity, the essential nature of the element doesn't change. Chlorine stays chlorine, whether it undergoes ionization, bonding, or whatever. And sodium retains its character of being sodium, but it goes through an ionization, and that is a change, right, of the element. But it doesn't change the essential properties of the element. When we talk about breaking down an element, that means changing it completely from, say, one element to something else. Well, that can't be done just simply by heating it or shining light on it or pouring other chemicals through it. And so the element retains its personal properties and its own personality, if you will. By definition, are the smallest entity of a substance that had specific chemical and physical properties but can be broken down into two or more component elements. By ordinary chemical means, chemical or physical means. We talk about what we call a decomposition reaction. Well, sodium chloride we've talked a little bit about. As a solid can be heated, delta over the arrow means heating is applied, something like 1150 degrees Celsius. This will go to sodium ions in the liquid phase. That means one's having a positive charge and the other having a negative charge. Now, if we take this and pass an electric charge through it, these will change into what we call basic elements in their standard state. And in this case, sodium metal neutralized and chlorine gas both neutralized. So we have, in essence, broken down a compound into its constituent elements, two or more of its constituent elements. And by simply passing an electric current through it, how it goes through that, you will visit and study in due time at the proper place. But the idea of organizing the study of chemistry from the complex to the simple is absolutely essential in the beginning of study in your course, because this is what we're going to do, is break it down to the simple and then build it back up. In the next class, what we'll do is start with atoms, talk about the atom structure, atomic structure, and what some of the terminology of the atom is, translate that to the periodic table and the elements and how it fits, and then talk about elements gaining and losing electrons at the valence level. You've heard of stuff like that. And so we start building it back up to the more complex in our work. So what the purpose of these initial comments are at this point are to show you that, well, when we study chemistry, our objective is to study matter. Well, that's everything in quite a collection. And so in order to study it systematically, we break it down to the simple and then build back up to the more complex.